Okay, welcome back. In this lesson, we are going to be covering Euler's method. This is a BC calculus only topic. What is Euler's method? It says, what happens when you can't solve for a particular solution of a differential equation? So up to this point, we've talked about slope fields and what a particular solution is. But what happens when you cannot solve for it? There is a method called Euler's method that's a numerical approach to approximating a particular solution of a differential equation. So when we use Euler's method, there is usually a step size for all the linear approximations. It is common to use a table, okay? dy dx is computed from the x and the y values. Sometimes it's just the y value, sometimes it's just the x value. Okay, you're given a differential equation, and each value of y is computed from the previous y and from the dy dx, from the previous dy dx values. So let's just take a look at something that we know from algebra. Okay, and this is going to help you remember Euler's method. So let me show you where it comes from. We have y minus y sub 1 equals m times x minus x sub 1. Hopefully that looks familiar to you. That is the point slope form of a line. Well, let's just call this change in y. So let's call it delta y. And let's call slope. What is a calculus notation for slope? Well, that would be dy dx. And then this is change in x. So we're just going to call that delta x. Okay? This change in x will be given, or you're going to find it. It's going to be your step size. Okay? So your change in y, we're going to calculate the change in y by taking the differential, which is going to be given, times the step size. And then we're going to find the y value for each individual step. Okay, so let's take a look at what that's going to look like. First thing we do is we make a table. Okay. You're given a starting point. You're given when y of 0 equals 1 is equal to 1.5. So you're given the point 0, 1.5. So what we're going to calculate next is, if you're starting at 1.5, what is your change in y if this is the given derivative? So again, your change in y is equivalent to the given differential, which is 3x minus 2y, times your step size. In this case, they want our step size to be 1. Okay? And then using that change in y, we can find the new y value. All right, so let's go ahead and calculate our change in y. It's 3 times the x value minus 2 times the y value, and all of that is going to be multiplied by our step size, which in this case is 1. Okay? So when we calculate this, we get 0 minus 2 times 1.5. That equals negative 3. So our change in y is negative 3. So if you start out at 1.5 and you add or subtract, add negative 3, your new y value is going to be negative 1.5. So that's the next y value for your step, in this case a step of 1. So this is the y value that goes with 1. Okay? Now they want us to approximate y of 2. So we have to keep going. So figure out your change in your y is going to be 3 times your x value minus 2 times, oops, I'm sorry, that's negative. Go back here. 2 times your new y value, and all of that is going to be multiplied by 1. So what is that? That's 3 plus 3, right? So your change in y is 6. So if you started at negative 1.5, and your change is 6, your new y value for your next step is 4.5. So again, our step size is 2. So the y value at 2 is 4.5. And that is the approximated answer for y of 2. Okay? All right, so that's Euler's method. Let's try another one. So we're going to start by making a table. Okay. All right, again, I'm going to write the change in y formula. The change in y is dy dx times change in x, again, which is your step size. What is with a step size of 0.5. So we're making our step size smaller. The smaller you make your steps, the more accurate you will be. Right? All right, so the given condition is 0, 1. Okay? If you want, we're going to 1.5, so with a half step. So if you want, you can fill in all of the x values right now if you want to. We're going to go up by a half. So our next step is going to be 0.5, then it's going to be 1, and then it's going to be 1.5. So those are the x values that we have, and we're going to calculate the y values using Euler's method. Okay, so the first change in y here is 2 times your x value minus your y value times 0.5. So that's what? 0 minus 1 times a half. So our change in y is what? Negative half or negative 0.5. Okay. So you started at 1 and you are changing by a negative 0.5. So your new y value is 0.5 or a half. Okay, so we have to keep going. So our next change in y is 2 times your x value of 0.5 minus your y value, in this case 0.5. And all of that is multiplied by your step of 0.5. So 2 times a half is 1. 1 minus a half is a half. And a half times a half is a fourth, or 0.25, whichever one you want to use. Some of these are going to require a calculator because the math is going to be a little hairy. Okay, so our new y value, we started at 0.5, and the change is a quarter, or 0.25. So our new y value for our next step is 0.75. So we're trying to find this y value. So let's go one more time. 2 times your x value minus your y value times your step size. All right, so when we calculate that, let's see, what do we get here? You can go ahead and use your calculator if you want to. What am I getting? I think I'm getting 5/8. Let me double check on my calculator here because I got a decimal. So 2 minus 0.75 times 0.5. Yeah, so 0.625 or 5/8. We'll just go with the calculator and use the decimal. So our new y value, again, we started at 0.75, and the change for this step is 0.625. So when you add that together, you end up getting your y value for your next step is 1.375. And there is your answer. Okay. Yeah. And if you kept it in fraction form, it would be 11/8. But again, for some of these, calculator is fine. Okay. Let's try one more. Why don't you kind of pause the video and see if you can try this one on your own. Okay, hopefully you gave it a try. If you didn't, pause it now and give it a try. I think this one is a little bit different because it says with 2 steps. With 2 steps. We're starting at 3, and they want us to go to 6, and they only want us to use 2 steps. So this one's a little bit different because they don't give us our step size. So we have to calculate our step size. Okay, so it's the difference in the x's divided by how many steps you want. So we're starting at 3, so it's 6 minus 3 divided by 2. So what's our step size? Step size is 1.5. That's an awfully big step size. We're not going to get very accurate by doing a 1.5 step size, but just be happy we only have to do 2 steps. Because that's a lot less work, but it's also a lot less accurate, okay? So we are starting at 3. The given y value is 1. So our change in y is calculated by dy dx. In this case, it's x minus y times our change in x, which is our step size of 1.5. And that will give us our new y value, or we can calculate our new y value. So let's go ahead and calculate our change in y. That is 3 minus 1 times your step size of 1.5. So that is 2 times 1.5. So what's 2 times 1.5? So we have a step size, or we have a change in y of 3. Well, we started at 1, and we have a change of 3. Our next y value for our next step, which is 1.5 later. So that's 4.5. The y value, the approximate y value is 4. Okay, well, let's go one more step. If we go one more step, we're going to be at 6. This is the y value we're trying to approximate. So let's calculate our change in y. 4.5 minus 4 times our step size. And what's that going to be? We're going to have a change in y of 0.75. So we started at 4. We have a change in y of 0.75. So our new y value for the next step is 4.75. Okay. Now, some of the questions that they may ask you is they may ask you if it's an underestimate or an overestimate. And again, if you watch the video, you would know that you have an underestimate if your curve is concave up, and you have an overestimate if your curve is concave down. Okay. They may also ask you to estimate a value using the tangent line to the curve. And again, you should know how to find the equation of a tangent line using the point. So let's say they wanted the tangent line at this point. Okay, well, if you're using this point, this is the slope at this point. So just remember, those types of questions do come up again sometimes. And remember your whole under and over estimates. And that is Euler's method.